The universe is filled with wonders. From the smallest atom to the largest galaxy, each element, no matter how minute or grand, plays a crucial role in the intricate tapestry of existence. We humans, with our insatiable curiosity, have always sought to understand and shape the world around us. This quest for knowledge and mastery has driven us to explore, innovate, and create. In this vast cosmic dance of creation, architecture stands as a testament to our ingenuity. From the ancient pyramids to modern skyscrapers, our built environment reflects our aspirations and achievements. It is the art and science of designing and constructing spaces that inspire, protect, and elevate the human experience. These spaces are where we live, work, and play, shaping our daily lives and our collective future. For centuries, architects relied on traditional tools like drawings and models to bring their visions to life. These methods, while effective, had their limitations in terms of precision and adaptability, but just as telescopes revolutionized our understanding of the cosmos, a new technology has emerged, transforming the way we design and build, Building Information Modeling, or BIM. This innovation is reshaping the architectural landscape. BIM is not merely a software or a tool, it is a paradigm shift in the world of architecture. It represents a new way of thinking, a holistic approach to design and construction that integrates every aspect of a building's life cycle. Imagine a digital universe where every line, every curve, every detail of a building is interconnected, alive with data. This interconnectedness allows for unprecedented levels of precision and collaboration. This is the essence of BIM. It is a comprehensive digital representation that encompasses not just the physical dimensions of a building, but also its functional and operational characteristics. It allows architects to create a virtual representation of a building, a digital twin that mirrors its physical counterpart in every way. This digital twin can be explored, tested, and refined long before construction begins. This virtual model is not just a static image, it is a dynamic, data-rich repository of information that evolves throughout the building's life cycle, from conception to demolition and even beyond. It ensures that every phase of the building process is informed, efficient, and sustainable, paving the way for a new era in architectural design and construction. In the past, architectural design and construction were often seen as separate, sequential stages. Architects would draft their designs, and then contractors would interpret those drawings to build the structure. This traditional approach often led to miscommunication, errors, and costly rework. BIM bridges the gap between design and construction, fostering a more collaborative and integrated approach. With BIM, architects, engineers, contractors, and clients can work together in a shared virtual environment. Imagine a virtual reality room where stakeholders can don their headsets and step inside the building. Before a single brick is laid, they can walk through the corridors, explore the spaces, and experience the design firsthand. This immersive experience allows for early detection of potential issues and facilitates better decision making. BIM also enables architects to perform complex simulations and analysis during the design phase. They can study the building's energy performance, structural integrity, and even its impact on the surrounding environment. This allows for optimization of the design for sustainability, efficiency, and cost effectiveness. The universe is governed by laws of physics, mathematics, and geometry. These fundamental principles shape everything around us, from the smallest particles to the grandest structures. Architects, inspired by these cosmic principles, have always sought to incorporate them into their designs. They strive to create buildings that not only serve functional purposes but also resonate with the natural order of the universe. Computational design tools empower architects to harness the power of computation to create innovative and complex forms that were once unimaginable. These tools open up new realms of creativity and precision, allowing for the exploration of designs that push the boundaries of traditional architecture. These tools allow architects to go beyond the limitations of traditional drafting software. They can experiment with forms and structures in ways that were previously impossible, leading to groundbreaking architectural innovations. They can generate designs based on algorithms, parameters, and data inputs. This means that architects can create highly customized and optimized designs that respond to specific environmental and functional requirements. Imagine designing a skyscraper that responds to the movement of the sun, optimizing daylight, and reducing energy consumption. Such dynamic and responsive designs are now within reach, thanks to computational design tools. One of the key aspects of computational design is parametric modeling. This approach allows architects to create flexible and adaptable designs that can easily be modified and optimized. This approach allows architects to define relationships between different elements of the design. By establishing these relationships, they can ensure that changes to one part of the design automatically adjust other related elements. For instance, changing the height of a wall can automatically adjust the size of the windows and the roof line, ensuring that the entire design remains consistent and coherent. This level of integration and coherence is crucial for creating harmonious and functional buildings. The computational design tools are not meant to replace the creativity of the architect. Instead, they serve as powerful aids that enhance the architect's ability to innovate and experiment. Instead, they act as an extension of the architect's mind, allowing them to explore a wider range of design possibilities and push the boundaries of what's possible. By combining traditional techniques with advanced computational tools, architects can create truly groundbreaking and visionary designs that shape the future of architecture. The universe is a complex tapestry of interconnected systems, each influencing and interacting with the others in a delicate balance. Everything from the orbits of planets to the behavior of subatomic particles can be described through the language of mathematics, a universal code that underpins the very fabric of reality. Visual programming languages like Dynamo for Revit and Grasshopper for Rhino bring this concept to the world of architecture, transforming abstract mathematical principles into tangible design tools. These tools allow architects to create and manipulate building information using a visual node-based interface, making complex design tasks more intuitive and accessible. Instead of writing lines of code, architects connect nodes that represent different functions and data inputs, streamlining the design process and reducing the potential for errors. Imagine a flowchart where each node represents a step in a process, and the connections between them define the flow of information. This visual approach simplifies complex tasks. For instance, an architect can use Dynamo to create a script that automatically generates a series of columns along a curved wall, ensuring precision and efficiency, adjusting their spacing and size based on the curvature of the wall, allowing for seamless integration of design and structural integrity. This not only saves time, but also ensures accuracy and consistency in the design, providing a higher level of quality control. Visual programming languages empower architects to automate repetitive tasks, generate complex geometries, and push the boundaries of traditional design. They enable architects to explore design iterations with ease, allowing for rapid prototyping and innovation. These tools are becoming essential for architects who want to embrace the power of computation in their design process, opening up new possibilities and efficiencies in the field of architecture